All right, so we're at 4 a.m. and now I'm starting a video on space weather data for earthquake prediction and the mixed reality model with artificial intelligence that I've been theorizing. And we've got 21 sources here, and I'm going to, oh, I have to load and delete the last one before I can have a new one. So yeah, basically been working out how to model a lot of pre-earthquake signals that have been identified by using hindsight analysis of 7 plus Richter earthquake uh, and new satellites and everything. So, all right, there we go. We can delete that one. Longer one because I've added new sources. All right, let's go. And I'll generate a new mind map as well. So, yeah, essentially, there's been so many new emergent pre-earthquake signals, but they're all kind of disparate and separate. They've all been done by hindsight analysis, and now there's an opportunity to bring them all into one, like, visual, humanized, understandable data model, and also have large language models and AI analyzing that for real-time feedback. And you can gamify it, customize the data feeds for real-time 24-hour news cycle, for earthquake prediction and alert models, for yeah, all manner of government and civil society and education and profitability and non-profit philanthropic uses. So if I get my mug out of the way, Space Weather News Hub. And yeah, I started coming up with this idea in 2023, after like years of watching Suspicious Observers and several other academic people, but it's 4 a.m. and I don't remember all their names. So if you come into, I'll put the link in the video description, but if you come into this, you can click on any of these icons. They'll open up more information, or like you can click on the actual mind map and it'll go back to the AI. The AI will query the data behind me, behind my mug, which is 21 documents in this, and then it'll come out with some content, and then you can obviously then click down into the chat bar. You can ask more comments, see it's coming out. It comes out with references, so you got more information. You can click on them, and this is Google's Notebook LM, which is really powerful for understanding large data sets and asking, like, meeting in the middle. Kind of, you're asking it questions from your knowledge base, and then you're consuming information, and it's a back and forth thing. So uh, it's amazing. But so the purpose is to integrate research, satellite and terrestrial data, interactive game scenes. We're currently just about to reach the peak of solar cycle 25, but it's not quite. The sun's polar fields haven't flipped yet, so we're nearing that. Make it in human-centric natural language, human experts, newsreaders, teachers, AI. Solar maximum, cycle 25 and going forward, because there's polarity flips and it can stuff up airline crews, climate change models. We're learning how to predict earthquakes and volcanoes and traditional weather. uh, generative AI integration, multimodal LLMs, virtual reality, condensed auto broadcasts for the news cycle and alerts, cross-platform support for extended reality, virtual reality, real-time data, like going into NASA, ESA, all of the main ones. India's got some really good satellites that are open source. There's all closed source, so we've got to kind of work between open source, closed sourced, and advanced visualizations and level of detail, 3D, 4D. So you can see that this is quite comprehensive, and even goes into future integrations, and like we haven't even really started with it yet. But rather than me waffling on about it, because it's 4 a.m. and I'm tired, I'd rather just show you that there's so much data in here that you can explore, and it's all clickable, it's all integratable with AI. At the video at the end, you'll be able to come and click into here. You can, you'll be able to click on any of these sources and look at the information in those sources. Click key topics, ask anything, chat with the AI, create it, look at the other mind maps, create mind maps, study guides, briefing docs, yada yada. And so it's a really powerful thing. And I'll just cut from here and put it onto the Notebook LM podcast. It's going to be probably 40 or 50 minutes that goes into really eloquent two people talking about all the deep dive data. So that'll be better than me being tired talking to you about it. So bye.
Welcome to the Deep Dive.
Great to be here.
Imagine a world where the sun's fiery breath stirs the Earth's very core, where the moon's subtle dance subtly shifts the ground beneath our feet, and where we can visualize these invisible cosmic forces.
Or even our own thoughts.
Exactly. Or even the intricate patterns of our own deepest thoughts in a fully immersive digital realm. It sounds like pure science fiction, doesn't it?
It truly does. And yet, as we have seen in the sources for today's deep dive, so much of that is either, well, already here or poised on the very near horizon. It's a breathtaking convergence of science and technology.
That's precisely right. Today, we're embarking on a truly fascinating deep dive into a stack of sources that reveal the profound, often surprising interconnections between cosmic phenomena, Earth's dynamic systems, and the cutting-edge technologies.
This stuff allowing us to understand, predict, even recreate these incredibly complex interactions.
Yes. Our mission is to extract the most important nuggets of knowledge from this remarkable convergence of space, Earth, and the digital frontier. So let's unpack this.
Okay, where do we start?
We're going to kick things off by looking up, way up, at the sun, our magnificent star, and the incredible cosmic orchestra it conducts. We'll begin with something called coronal holes and the solar wind.
Which our sources often describe as essentially the sun's breath.
Right. What exactly are these phenomena, and why should we, down here on Earth, care about them?
Well, what's truly fascinating here is just how directly connected these seemingly distant solar phenomena are to our everyday lives. Coronal holes are identified as these darker, cooler, less dense patches on the sun.
You see them best in certain kinds of light, right? UV and X-ray.
Exactly, particularly visible when observed in extreme ultraviolet and X-ray radiation. To visualize them, think of them as vast, temporary open doorways or maybe thin spots in the sun's outer atmosphere, the corona.
Yep.
These doorways are regions where the sun's magnetic field lines don't loop back to the surface like they normally do. Instead, they sort of extend outwards into interplanetary space.
So they're open-ended.
Precisely. And this configuration allows a continuous high-speed stream of solar plasma, what we call high-speed solar wind, or HSSs, to escape directly into space at incredible velocity.
High speed indeed. Our sources indicate these HSSs can travel at astonishing speeds, ranging anywhere from 300 to a staggering 800 kilometers per second.
Yeah, that's hundreds of miles per second. It's hard to even wrap your head around speeds like that.
So, if these are essentially the sun exhaling these incredibly fast streams, what's the real significance for us down here on Earth? Why is this something we need to monitor so closely?
Their significance cannot be overstated, really. While they might appear as, distant solar phenomena, these high-speed solar winds are absolutely crucial drivers of what we call space weather.
Right, Smother.
They carry energy and magnetic fields towards Earth, having direct, measurable implications for our planet. Space weather, as we'll get into more detail on, impacts everything from our cutting-edge technology, the very infrastructure of our modern world, to potentially even the ground beneath our feet and the natural world around us.
So anticipating them is key.
Absolutely. Anticipating these events allows us to mitigate potential disruptions.
And what's truly remarkable, from what I've been reading, is how our ability to understand and predict these coronal holes is rapidly evolving. It's no longer just about detecting that one exists, is it? We're moving into a much more proactive phase.
That's a crucial distinction. The cutting edge of prediction in this field is truly remarkable and represents a significant leap forward. Historically, detecting coronal holes relied heavily on, manual inspection of satellite imagery.
Which sounds tedious and maybe prone to error.
Exactly. As you can imagine, it could be inconsistent and time-consuming due to human subjectivity and just the sheer volume of data. But new research is revolutionizing this.
How so? AI, I assume.
You got it. They're now utilizing advanced deep learning models, specifically long short-term memory, or LSTM networks. These are sophisticated neural networks trained on vast data sets of solar observations.
And they're using them for predictive modeling.
Yes, predictive modeling of coronal hole dimensions and characteristics. This means we're moving from merely knowing a coronal hole exists after it forms to actually forecasting its size, shape, and behavior up to 7 days in advance.
7 days. Wow.
Yeah. Our sources describe this as a pioneering approach because it fundamentally shifts the paradigm from simple reactive detection to proactive, crucial forecasting.
7 days in advance. That's a massive lead time in the world of space weather. So, what does this all mean for you, the listener, in practical terms? Why does being able to anticipate these HSSs matter so profoundly for our daily lives and global infrastructure?
That 7-day lead time is transformative, honestly. Being able to anticipate these high-speed solar winds gives us a vital window to prepare. Think about critical infrastructure.
Like satellites, power grids.
Exactly. Satellite operators can put their assets into safe mode or reorient them to minimize exposure. Power grid managers can adjust loads or initiate protective measures against potential surges. Airlines can alter flight paths to avoid communication blackouts over polar regions.
Even things like GPS accuracy.
Definitely. Even emergency services can be put on higher alert for potential GPS degradation. This foresight is critical for safeguarding our technological infrastructure, ensuring continuous operation of vital services, and minimizing economic impacts from space weather events.
Right. It moves us from just reacting.
Exactly, from merely reacting to these cosmic forces to proactively managing their potential consequences.
Speaking of those impacts, let's clarify some terms that often get discussed when we talk about the sun's activity. Solar flares, coronal mass ejections, or CMEs, and geomagnetic storms. They're often grouped together, but how are they truly different, and what distinct impacts do they have on Earth?
That's an excellent question, as they are often conflated but have important distinctions that are vital for understanding space weather. Solar flares are rapid, intense bursts of electromagnetic radiation and energy in the sun's atmosphere.
Like a flashbulb going off.
Yeah, think of them as a sudden, brilliant flash of light across the entire electromagnetic spectrum, from radio waves to X-rays. They travel at the speed of light, so they reach Earth in about 8 minutes.
8 minutes, okay. And CMEs.
CMEs, on the other hand, are massive expulsions of solar plasma and magnetic fields, literally billions of tons of solar material hurled into space.
So not just light, but actual stuff.
Exactly. While flares are about radiation, CMEs are about a physical mass of charged particles, and they travel much slower, typically taking 1 to 3 days to reach Earth.
So one is a flash of energy, the other is a giant cloud of electrified gas. That clarifies it. And our sources point out a fascinating distinction in their impacts, particularly on geomagnetic storms.
Yes, understanding this distinction is key. What's truly fascinating here is how the geomagnetic storms driven by CMEs differ from those caused by the high-speed solar winds from coronal holes we just discussed.
How so?
CME-driven storms tend to be very large and abrupt, like a sudden, powerful shock wave hitting Earth's magnetic field. They typically peak during the solar maximum, the period of highest solar activity when large, active sunspot regions are more common.
Okay, big and sudden. And the HSS storms.
HSS-driven storms, while typically weaker in their instantaneous intensity or initial impact, are far more prolonged. They can last for days or even months as Earth continually passes through the stream.
Days or months.
Yeah, they're more common during the declining phase of the solar cycle, when large coronal holes become more stable and persistent. One source even notes a striking statistic. Between 1996 and 2011, there were 379 HSS-driven storms compared to only 62 CME-associated ones.
Whoa, that's a huge difference.
It indicates their significantly greater geo-effectiveness over time, meaning they are more consistently and cumulatively impacting Earth despite their lower individual intensity.
That's a really important point. The slow burn can have a bigger total effect. And how do we even measure the intensity of these geomagnetic storms once they reach Earth?
We use various indices, but the most common is the K-Pay index. It's a planetary index, basically a scale from 0 to 9.
And higher is worse.
Right. Anything 5 or above is considered a significant geomagnetic storm. A KP of 5 indicates a moderate storm affecting some power systems and satellite operations. A KP of 7 to 8 is a strong to severe storm.
Sounds serious.
It is, potentially causing widespread power outages and satellite failures. And a KP of 9, the highest, represents an extreme storm, which could have catastrophic global impacts.
So this index translates the energy into a practical measure of impact.
Exactly. It helps scientists and operators quantify the disturbances in Earth's magnetosphere caused by these solar events.
So what does this all mean for us? Beyond just a number on a scale, how do these disturbances truly affect our daily lives, and what kinds of tangible impacts do they have?
These disturbances have tangible effects that ripple through our modern interconnected infrastructure. They can disrupt navigation systems, leading to errors in GPS accuracy.
It impacts tons of things, right?
Yeah.
Farming, planes, maps.
Everything from precision agriculture and mapping to air traffic control and emergency services. They can cause outages in satellite communications, affecting global broadband, broadcasting, and military operations.
And the power grid.
Crucially, yes. They can induce currents in long conductors like power grids and pipelines, potentially leading to transformer damage, protective relay trips, and widespread blackouts.
And the auroras. That's the pretty part, I guess.
They are also responsible for the stunning auroras, the northern and southern lights, but our sources suggest these auroras can extend much further from the poles than we typically imagine during strong storms.
So that indicates a bigger impact zone, really.
Precisely, a broader reach of these geomagnetic impacts on Earth's upper atmosphere.
And this leads us to where it gets really interesting, I think. Our sources delve into something called joule heating. This isn't just about pretty lights. It's a direct, almost hidden influence on Earth's climate that many might not be aware of. Can you break down what joule heating is and why it's such a critical, yet potentially overlooked factor?
Yeah, joule heating refers to the direct injection of solar wind energy into Earth's upper atmosphere, specifically the thermosphere and ionosphere. Imagine it as an electrical heating effect.
Like a giant space toaster coil.
Sort of. When the solar wind's charged particles and magnetic fields interact with our planet's magnetosphere, they induce powerful electrical currents in the upper atmosphere. As these currents flow through the atmospheric gases, they generate heat.
Just like electricity heating a wire.
Exactly. Through a process similar to how electricity heats the filament in an old light bulb or coil in a toaster, this heat is then directly transferred to the atmospheric gases. During geomagnetic storms, this joule heating vastly increases, dramatically raising the temperature of the upper atmosphere.
And that heat doesn't just stay up high.
No, and that's the crucial part. This energy then integrates into the lower atmosphere for days, not just fleeting moments. This makes it a significant, yet often overlooked, component of how the sun influences our climate system. It's a direct energy input that affects atmospheric dynamics.
And this is where it becomes quite thought-provoking, isn't it? Our sources highlight a significant gap in our current understanding, or perhaps our willingness to incorporate this data into broader scientific models.
Indeed. A critical gap identified by our sources is that despite no fewer than 4 major studies since 2018 reaching the exact same conclusion about this phenomenon's significant underestimation in climate models.
4 studies, that seems like a lot.
It is 4 major studies all saying the same thing. Yet there has been no clear indication that official climate modelers intend to include it, or at least fully account for it, in future projections.
Which raises a huge question.
It raises a profound and important question. If this significant natural driver of atmospheric variability, this direct injection of solar energy into our lower atmosphere, is being underestimated or completely omitted from our most sophisticated climate models, what does it mean for the accuracy and completeness of our current climate change models and their long-term projections?
Right. It suggests a potential blind spot.
It suggests a potential blind spot in our comprehensive understanding of Earth's climate dynamics, particularly when trying to disentangle natural variability from anthropogenic influences. It's a scientific puzzle that calls for greater integration across disciplines.
That's a truly thought-provoking point. It makes you wonder what other hidden cosmic influences are out there impacting our planet. Moving from direct heating, let's talk about magnetic fields and hydrology. Our sources suggest that our planet's shifting magnetic field has surprising connections to global rain patterns and temperature shifts. This is a very different kind of solar influence.
It adds another layer to this intricate cosmic influence. Beyond direct energy input like joule heating, the fluctuations in solar and cosmic radiation are identified as primary drivers of Earth's broader temperature variations over, geological timescales.
And the magnetic field plays a role in that.
Yes. New research highlights how magnetic pole shifts, like the one Earth is currently undergoing, and which our sources confirm is accelerating, directly influence global rain patterns and temperature distribution.
The pole shift is accelerating.
Apparently so. And this isn't just about where your compass points, it's about the strength and configuration of Earth's entire protective magnetic shield. Changes in this shield can alter how cosmic rays penetrate our atmosphere.
And cosmic rays can affect clouds.
That's the theory, potentially affecting cloud formation and, by extension, precipitation patterns.
An accelerating pole shift, influencing rain and temperature. What are the broader implications of understanding this phenomenon for our future?
The implications are indeed profound. Our sources indicate that some of the key changes seen in the past are showing signs of beginning again now.
Like history repeating itself, driven by magnetism.
Potentially. It suggests that by understanding these accelerating magnetic field shifts and their historical correlations with climate, we could gain vital insights into future hydrological cycles and temperature patterns. It provides another crucial piece of the puzzle for predicting Earth's environmental changes.
Suggesting some changes might be natural, not just human-caused.
Exactly. It suggests that some shifts we observe might have a natural geomagnetically driven component that needs to be factored into our long-term climate predictions.
To truly grasp the scale of solar activity and its potential impacts, sometimes we need to look back in time at extreme events. Our sources bring up the Carrington event from 1859, a monumental solar flare. What was it, and what new historical context have we recently uncovered about its true scale?
The Carrington event in 1859 was arguably the most powerful observed solar storm in recorded history. It was described as an X80 power superflare.
X80. X-class is already the biggest category.
Right, so X80 is almost unfathomably powerful. It caused widespread auroras, visible even in tropical latitudes like Cuba and Hawaii, and generated telegraph system fires.
Which was a high-tech of the day.
Exactly, impacting the limited technological infrastructures of the time. What's historically significant is that while other past extreme solar events had left telltale signatures in the carbon content of ancient tree rings, like distinct spikes in carbon-14 levels, direct carbon-14 evidence for the Carrington event itself was surprisingly missing from these records.
Yeah, it was missing. That seems odd.
It did, until very recently.
Until now, you say. So what's this new discovery that changes our understanding of the Carrington event's true magnitude and its implications for today?
Scientists have now found the unequivocal carbon-14 signature of the Carrington event in polar tree rings. This discovery provides a direct and independent proxy for its true scale and energy release.
Ah, so the evidence was there, just harder to find.
It seems so. It's a remarkable confirmation. This historical insight is absolutely crucial for assessing our current vulnerability to similar extreme events today, given our much greater reliance on fragile technological infrastructures.
Yeah, an event like that today would be catastrophic.
Potentially, yes. It's a stark reminder that while these black swan events are rare, they are a fundamental part of Earth's cosmic environment, and we need to understand their potential to prepare for future solar eruptions.
Okay, so we've delved into the sun's powerful influence and historical precedents. Now let's bring it back down to Earth, specifically to Earth's tremors, and unpack how cosmic activity and other emerging precursors might help us predict earthquakes. This leads us to a profound area of study, the solar seismic link. What's the correlation being found between solar activity and seismic events?
This is truly a profound discovery that has gained significant traction over the last decade of study, shifting from, let's say, speculative hypothesis to increasingly robust evidence.
So it's becoming more accepted.
It seems to be. Our sources indicate a clear and compelling correlation between various forms of solar activity, including flares, solar wind, proton flux, streams of high-energy protons, and geomagnetic storms and seismic activity on Earth.
How strong is the evidence?
Some research shows conclusive evidence of increase in tectonic activity following solar flares, with a notable 38% increase in activity over 10 days in the Earth-facing area directly opposite where the flare erupts.
Opposite the flare. That's specific.
It suggests a mechanism where intense solar energy hitting Earth's magnetosphere can induce stress on tectonic plates, perhaps focused magnetically.
A 38% increase in activity after a solar flare is quite significant. And there's also a negative correlation involved, which sounds counterintuitive in this context. Can you elaborate on that?
It is indeed. What's fascinating here is the finding of a significant negative correlation between the sunspot number and the global seismic energy release, especially during the decay phase of the solar cycle.
Oh, no, fewer sunspots means more earthquake energy.
That's what the data suggests. It means that as sunspot numbers decrease after the solar maximum and the sun becomes less active in terms of flares, global seismic energy release actually tends to increase.
Why would that be?
Well, it suggests a more nuanced and complex relationship than just direct boosts in activity. Perhaps during periods of lower solar activity, the solar wind streams from coronal holes become more stable and persistent.
Like that steady HSS stream we talked about.
Exactly. Providing a long-term, subtle, but cumulative stressor on Earth's tectonic plates, leading to a greater release of seismic energy over time. It adds a layer of complexity to the solar seismic link, showing it's not a simple linear relationship.
Are there any specific major earthquake examples that really illustrate this solar seismic connection, making it more concrete for us?
Absolutely. Our sources provide compelling examples that underscore these findings. The devastating M9.1 Japan earthquake in 2011, for instance, was notably preceded by high-speed solar wind streams from an enlarged coronal hole that continuously buffeted Earth's magnetosphere.
Right, I remember reading about that connection.
Similarly, the M7.6 Chichi Taiwan earthquake in 1999 saw significant ultra-low frequency, or ULF, wave activity detected prior to the event, which was then linked to solar rotation periods and a strong coronal hole-driven geomagnetic storm.
So these aren't just isolated incidents.
It suggests a consistent pattern that researchers are actively investigating to understand the precise physical mechanisms at play.
So why does understanding this intricate solar behavior matter so much when we're trying to forecast seismic risks? What's the practical upshot for disaster preparedness?
It suggests that understanding solar behavior could be a key, perhaps even an essential piece of the puzzle in forecasting seismic risks. While we're still far from precise earthquake prediction based solely on solar activity,
Yeah, we're not there yet.
no, but these correlations provide a potential avenue for what we call nowcasting, or even probabilistic forecasting. If we can accurately predict solar events and their characteristics, we might gain valuable lead time, or at least a heightened awareness of potential seismic activity in vulnerable regions.
So better warnings, maybe.
Possibly. This could inform public awareness campaigns, trigger pre-disaster checks on critical infrastructure, or even guide the deployment of emergency resources, improving our overall resilience to natural disasters. It's about building a multi-layered warning system.
Beyond these cosmic influences, researchers are also listening directly to Earth's whispers for new earthquake precursors. What kind of atmospheric and ionospheric anomalies are they identifying as potential signals that the ground is about to shake?
Right, beyond the cosmic influences, researchers are indeed identifying more direct earthquake precursors within Earth's own complex systems. This includes detecting subtle stratospheric temperature anomalies, unusual warming or cooling patterns high above us.
Changes way up in the stratosphere.
Yes, and also ultra-low frequency, ULF, radio emissions emanating from the ground. These are being observed using sophisticated ground-based sensors and satellites, like the China Seismic Electromagnetic Satellite, or CSES.
What's the theory there? Stress causing emissions.
The theory is that as tectonic plates undergo immense stress before an earthquake, they can generate these electromagnetic signals and alter atmospheric conditions.
And what about disturbances in the ionosphere, that electrically charged layer high above us, even beyond the stratosphere? How are those being monitored?
Global Positioning System, or GPS, satellite data is proving incredibly valuable here. By analyzing GPS signals, researchers are able to detect subtle shifts and fluctuations in the equatorial ionospheric anomaly, EIA, north crest, before seismic events.
So GPS can detect ionosphere changes.
It can. To visualize this, imagine the ionosphere as a dynamic, electrically charged blanket. When the Earth's crust is under extreme stress, it can generate abnormal electric fields that propagate upwards, almost like ripples.
Ripples going up from the ground.
Exactly. These ripples then disturb the ionosphere, causing detectable changes in its density and structure, which GPS signals can pick up. This highlights what scientists call seismo-ionospheric coupling mechanisms, the idea that there's a dynamic physical link between the lithosphere, Earth's crust, the atmosphere, and the ionosphere that can convey pre-earthquake signals.
Wow. Lithosphere, atmosphere, ionosphere coupling. LAIC.
That's the term, yes.
So what does this all mean for us? How do these findings, these subtle whispers from the atmosphere and ionosphere, contribute to our ultimate ability to predict earthquakes?
Well, these findings underscore the emerging and incredibly promising field of LAIC. It hints at the potential for sophisticated real-time monitoring systems that could anticipate earthquakes based on these subtle atmospheric and ionospheric signals.
Like a network of sensors listening for these whispers.
Exactly. Imagine a system that's constantly listening to these whispers from the Earth and its upper atmosphere, integrating data from a global network of sensors, providing early warnings or at least a heightened probability of seismic activity.
Still research, but promising.
Very much so. While still an active area of research, it represents a significant step towards leveraging the interconnectedness of Earth's systems for disaster prevention.
To get an even more complete picture, we need to bring in more traditional geological insights. Our sources talk about multi-layered monitoring for hidden signals directly from the Earth itself. What are some of these detailed geological precursors being watched on the ground?
Right. Our sources indicate a suite of detailed geological precursors being monitored, complementing the atmospheric observations. These include measurable increases in radon emissions from the ground.
Radon gas, like from basements.
The same gas, yes, it can surge as rocks crack under stress. Also, unusual animal behavior, though this is harder to quantify scientifically.
Yeah, the anecdotal stuff.
Right. Also, observable changes in water levels in wells, which can fluctuate due to ground deformation, and subtle ground deformation detected by advanced technologies like interferometric synthetic aperture radar, or INSAR.
INSAR, that uses satellites.
Yes, INSAR uses satellite radar to measure ground surface changes down to a centimeter, revealing how the Earth's crust is deforming over time, a crucial pre-seismic indicator. These are all subtle signs that the Earth's crust is undergoing immense stress before a major event.
And here's where it gets really interesting with radon. I heard it has a unique role, almost influenced by invisible fields beneath the surface. Can you explain that?
It does, and it's a fascinating hypothesis. Radon gas being both diamagnetic,
Meaning it's repelled by magnet.
weakly repelled, yes,
Yeah.
and it's non-conductive, so it's hypothesized to be influenced by local electromagnetic fields within the Earth's crust.
How would those fields get there?
As rocks are stressed and fractured before an earthquake, they can generate what are called piezoelectric effects, creating small electrical charges or localized electromagnetic fields.
Ah, stress creating electricity.
Exactly. If radon's movement and accumulation are indeed influenced by these changes in electromagnetic fields, then monitoring these subtle field variations could offer new, valuable insights into radon's behavior as a seismic indicator, going beyond just its concentration.
So watching the fields in the gas.
Potentially, yes. It's a compelling intersection of geology and electromagnetism that could unlock new ways to interpret this precursor.
Are there any other subtle indicators that complete this multi-layered monitoring approach, painting an even richer picture of what's happening underground?
Yes, there are several more sophisticated techniques and observations. Thermal infrared imaging, often from satellites, can detect minute ground temperature changes.
Heat changes from gas or fluids moving.
Potentially linked to rising underground gases or fluids, a possible heat signature of increasing subsurface activity. Acoustic emission analysis in rock media provides insights into stress levels by literally listening to the tiny cracking sounds rocks make under increasing pressure.
Listening to rocks crack.
Wow. Recorded by specialized sensors, yes. And interestingly, while often anecdotal, even community-reported observations of peculiar sounds, strange lights, or changes in pet behavior, though requiring careful scientific validation, can sometimes be correlated with scientific data.
So even those stories might hold clues sometimes.
If interpreted correctly within the broader scientific context, they can add a unique layer of detail.
So what's the relevance of integrating all these incredibly diverse data streams, from satellite observations to animal behavior?
When integrated, these diverse data streams provide a comprehensive, multifaceted picture of potential pre-earthquake phenomena. No single indicator is perfect, right?
Right, no silver bullet.
Exactly. But by combining information from atmospheric anomalies, ionospheric disturbances, ground deformation, gas emissions, and even subtle electromagnetic shifts, we can begin to build a far more robust and reliable picture of potential seismic activity. It's about combining every possible whisper and tremor the Earth gives us to build a more robust understanding and, hopefully, a more effective warning system.
To truly grasp Earth's tremors, we can't just look at the surface or its atmospheric interactions. We need to peer into the deep interior. Understanding Earth's core and mantle is fundamental. What kind of data are scientists integrating to achieve this deeper understanding of our planet's inner workings?
Well, to gain this deeper understanding, scientists are integrating a wide array of geological and geophysical data. This includes detailed reports from mining companies, which offer invaluable on-the-ground insights into deep geological formations and rock properties.
Data from drilling deep.
Yes, and they also analyze core samples extracted from deep drilling projects, providing direct information on the composition, structure, and age of rock formations thousands of meters below the surface. Crucially, they study deep Earth anomalies like low shear velocity zones, or LSVZs, and large low shear velocity provinces, or LSVPs.
LSVZs and LSVPs? Those sound complex. What are they?
They aren't just obscure terms. Imagine them as vast, irregular mountains or maybe continents of unusually hot, dense rock, sometimes thousands of kilometers wide and hundreds deep, residing just above the Earth's core.
Giant blobs down there.
Essentially, yes. Understanding their behavior helps us map the deep Earth convection currents, which are the fundamental drivers of plate tectonics and ultimately earthquakes at the surface.
And our sources mention a special case mineral, olivine. Why is this particular mineral so critical in understanding Earth's inner workings, especially its mantle?
Olivine is highlighted as a critical mineral due to its sheer abundance in the upper mantle, making up a significant portion of its volume. Its unique properties, particularly how it behaves under immense pressure and temperature, profoundly influence the mantle's rheology.
Rheology, meaning how it flows.
Its flow and deformation characteristics, exactly. Olivine's ability to deform plastically or flow over geological timescales is crucial for understanding how the mantle convects, and consequently, its crucial role in driving plate tectonics.
So understanding olivine helps understand plate movement.
Yes. Understanding olivine's crystalline structure, its phase transitions, and its distribution is essential for comprehending how the Earth's mantle moves and drives surface processes like volcanic activity and seismic events. It's like understanding the gears in a massive, slow-moving engine.
So why does this deeper geological insight into things like olivine and mantle anomalies matter for us in terms of understanding and potentially predicting earthquakes?
This deeper geological insight is absolutely essential for building more complete and accurate models of plate tectonics and ultimately seismic activity. By understanding the processes driving the movement of continents and the stresses building up in the crust, we can better assess seismic hazards.
The better we know the engine, the better we predict its effects.
Precisely. The more we understand the fundamental engine of our planet, from its innermost core to its outer crust, the better we can predict its effects and prepare for the powerful tremors it generates.
Let's talk about the current state of earthquake prediction. It sounds like a blend of incredible ambition meeting the complex reality of Earth's systems. What's the ultimate ambitious goal researchers are striving for in this field?
The ultimate objective, as our sources highlight, is incredibly ambitious: to predict magnitude 7 or greater earthquakes with a 1-hour warning and within 100 kilometers of the epicenter.
A 1-hour warning for a major quake, that would be Huge.
An absolute game changer for disaster preparedness, yes. Allowing for mass evacuations or protective measures to be taken with vital lead time, potentially saving countless lives.
That sounds like a monumental, almost impossible task, given how unpredictable earthquakes have traditionally been. What are the current challenges that prevent us from reliably achieving such precise predictions, and what kind of promise does the ongoing research hold?
You're right, it is a monumental task. While current research, combining space weather insights and various geological precursors, shows significant promise in correlating these signals with seismic activity, reliably achieving such precise predictions remains, well, elusive.
Why is it so hard?
It's primarily due to the chaotic nature of seismic processes. The Earth's crust is incredibly complex, with countless interacting faults and stress fields. We also have an incomplete understanding of precursory phenomena. We're still learning exactly what signals to look for, how to interpret them, and when they translate into an imminent earthquake.
Like listening for one specific whisper in a noisy room.
That's a good analogy. It's like listening to thousands of whispers and trying to discern which one is the actual warning.
So, if it's so challenging, what's the path forward? What gives us hope that we can push the boundaries of what's currently possible in earthquake prediction?
The sources emphasize that by consolidating diverse data sets from solar observations and ionospheric disturbances to ground deformation and radon emissions into a single real-time analysis framework.
Bringing it all together.
Yes, and enhancing that framework with powerful machine learning algorithms, we can indeed push the boundaries of what is possible. Machine learning excels at finding subtle patterns in vast amounts of data that are too complex or nuanced for human observation alone.
So AI can help find the patterns we miss.
That's the hope. This approach, leveraging cutting-edge AI, is a testament to human ingenuity and our relentless pursuit of knowledge, aiming to transform our reactive stance into a more proactive one in the face of seismic hazards.
And this pursuit of knowledge is brilliantly showcased by events like the Global Earthquake Prediction Hackathon. This isn't just about scientists and labs, it's about community innovation on a grand scale, isn't it?
It absolutely is. This hackathon is a fantastic, dynamic example of community innovation in action. It's a virtual event that brings together students, researchers, and industry experts from every corner of the planet.
A global brainstorm, basically.
You could call it that. It's designed to be a virtual concoction of innovation, where diverse minds, often from different disciplines, connect through technology and collaborate intensely. Instead of working in silos, they're pooling their collective intelligence.
And what's the core mission here? How is it accelerating solutions beyond traditional scientific methods and timelines?
Its mission is clear: to forge solutions for Earth's pressing challenges, particularly in disaster prevention and recovery, at an accelerated pace. Crucially, it aims to bypass the often traditional slow processes of government grants and academic cycles by fostering rapid, ad hoc innovation.
Cutting through the red tape.
In a sense, it's described as a celebration of human ingenuity, aiming to knit a global network of future collaborators who can respond quickly to real-world problems. Participants are challenged to analyze complex data sets, develop new algorithms, and build prototypes for predictive tools, all within a compressed time frame.
So why does a hackathon like this matter? What's the broader significance for addressing these existential threats that our planet faces?
This hackathon embodies the spirit of collective effort and rapid innovation needed to address what are essentially existential threats to life on Earth through technology. It's not just about competition. It offers participants new skills, insights, and potential career opportunities.
Building the next generation of problem solvers.
Exactly. Proving that when diverse minds come together with a shared purpose and the right tools, they can make profound differences. It demonstrates how leveraging a global network of talent can accelerate breakthroughs in areas like earthquake prediction, ultimately contributing to saving lives and building more resilient societies. It's about leveraging human ingenuity to solve our biggest planetary challenges.
That's a powerful way to bring the human element into predicting Earth's great forces. We've covered the sun's fury and Earth's subtle warnings. Now let's explore another celestial body that's much closer to home and has a profound, yet often underestimated, influence on our planet, our moon. We'll start with something we all know: tidal forces, but there's a fascinating, potentially deeper layer our sources reveal. What's the known interaction between the moon and Earth when it comes to tides?
Right, we're all familiar with how the moon's gravity causes ocean tides, the rhythmic ebb and flow of the sea that we see daily. What's often less intuitive, but equally fascinating here is how these immense gravitational forces also cause tidal bulges in Earth's solid crust itself.
The ground actually bulges.
Yes, subtle but continuous deformations of our planet's ground, like the Earth is gently stretching and compressing. These crustal bulges subtly stress fault lines and can potentially influence tectonic movements, acting as a constant underlying force on geological features,
Especially near coastlines or fault lines.
particularly along coastlines and major fault zones that are already under stress.
So it's not just the water that's affected by the moon's pull, but the very ground we stand on. How can we visualize this unseen constant stress on the Earth's crust? It's hard to imagine something so subtle having a significant impact.
Well, to visualize this unseen force, imagine the Earth's surface with invisible wavy lines that represent the subtle rise and fall of the solid ground, much like ocean tides. Now, picture how this immense, continuous gravitational pull from the moon applies stress to geological features.
Like kneading dough, but really, really slowly.
That's a good way to put it, like a rhythmic, almost imperceptible kneading of the Earth. Along existing fault lines where tectonic plates meet, this constant subtle stress can incrementally contribute to the buildup or release of strain.
So maybe it could trigger a quake sometimes.
While individual tidal stresses are small, their cumulative effect over time, especially when combined with other geological forces, is a subject of active research for its potential influence on triggering seismic activity.
This raises an important question. What if there's more than just gravity at play in the Earth-Moon interaction? Our sources propose a provocative hypothesis about a significant electromagnetic influence that could extend beyond simple tidal forces.
This is where the discussion truly opens up into a new frontier of understanding. A compelling hypothesis suggests that Earth-Moon interactions involve significant electromagnetic components in addition to the well-understood gravitational forces.
Electromagnetic.
The idea is that as the moon orbits our planet, it doesn't just experience Earth's gravity, it also passes through varying intensities of Earth's magnetotail, that elongated portion of our magnetic field stretched out into space by the solar wind, and the broader solar electromagnetic field.
So it's flying through different magnetic zones.
Exactly. This constant traverse through different magnetic environments could induce electromagnetic interactions between the moon and Earth, acting as a dynamic, invisible tether.
And what's the hypothesized impact of this electromagnetic interaction on things like tides, or even more remarkably, on terrestrial weather patterns?
Well, this electromagnetic interaction is hypothesized to influence tidal dynamics beyond traditional gravitational explanations, suggesting that some observed tidal anomalies might have an electromagnetic component.
Okay, affecting tides, but weather.
Yes, and this is the more radical part. It's also suggested to have a measurable impact on the formation and behavior of atmospheric vortices, like cyclones, hurricanes, and large-scale pressure systems.
Whoa! The moon affecting hurricanes electromagnetically.
The theory is that changes in Earth's magnetosphere, influenced by the moon's passage through it, could subtly alter atmospheric conductivity or energy flow, thereby affecting the development and intensity of these weather systems. It's a bold claim that challenges conventional meteorology.
If we connect this to the bigger picture, this theoretical framework, if proven, could truly revolutionize our understanding of how celestial mechanics influence terrestrial weather. It suggests that it's not just about the sun, but the moon too, playing an active, perhaps electromagnetic role in shaping our climate.
Exactly. It adds a whole new dimension to Earth's atmospheric science and climate modeling, suggesting that the moon is not just a gravitational partner, but potentially an electromagnetic one, with far-reaching consequences for our weather systems.
So we might need to rethink weather models.
If this hypothesis holds true, it means we might need to fundamentally rethink how we model and predict weather, incorporating these subtle but persistent lunar electromagnetic influences. It's an exciting, albeit challenging, area of research.
To validate such groundbreaking hypotheses, especially about electromagnetic influences between celestial bodies, scientists need concrete ways to test them. Our sources suggest using plasma experiments as lab analogs for cosmic phenomena. How exactly would this work in a controlled laboratory environment?
Right. To test these complex and theoretical interactions, researchers propose replicating similar force conditions, such as magnetic fields, plasma densities, and gravitational analogs in controlled laboratory environments.
Like building a mini Earth-Moon system in the lab.
Essentially, yes. creating miniature cosmic scenarios right here on Earth, using high-energy plasma chambers or specialized devices that can simulate the magnetic and electrical environments found in space. The goal is to isolate and observe the specific electromagnetic interactions that are hypothesized to occur between Earth and the Moon.
And what's the ultimate goal of bridging this gap between theoretical physics and practical experimentation? What kind of breakthroughs could come from these lab analogs?
The goal is to provide empirical evidence for or against these groundbreaking hypotheses. By observing comparable effects in plasma that may mirror those in the Earth's atmosphere or between celestial bodies, scientists can test these complex interactions in a measurable and controlled way.
So lab tests could prove or disprove the theory.
Potentially, yes. This could lead to significant breakthroughs in both space weather forecasting by better understanding how the Moon influences our magnetosphere, and Earth science by clarifying its impact on our atmosphere and even tectonic activity. It's about taking abstract theoretical frameworks and subjecting them to rigorous experimental validation, pushing the boundaries of our understanding of cosmic influence.
We've covered the cosmic forces and Earth's responses, even the Moon's subtle dance. Now let's step fully into the digital frontier, where virtual reality and artificial intelligence are transforming how we understand, interact with, and even perceive this complex data. This brings us to the Space Weather News Hub, which sounds like news delivery at the very frontiers of VR. What's this new paradigm for consuming critical information?
This is where all this incredible complex data truly comes together in a revolutionary way. Our sources describe a groundbreaking educational initiative being developed. A VR space weather news reading studio.
A VR news studio for space weather.
Exactly. This isn't just a static display, it's a fully immersive environment that integrates generative AI or Gen AI and advanced multimodal large language models, or LLMs, to deliver factual reporting and live data about space weather.
And it's timely, with the solar cycle peaking soon.
Very timely. Solar sunspot cycle 25 is projected to peak in mid-2025, bringing increased solar activity and a greater need for real-time information.
An immersive news experience. That sounds incredible. What does it actually feel like to be inside this virtual studio consuming space weather news?
You'll step into a virtual studio described as sleek and modern, a hub where you're surrounded by dynamically updating information. Imagine standing before a massive holographic globe of Earth rotating majestically with real-time overlays of atmospheric data.
Like a sci-fi movie control room.
Pretty much. Beside it, a live feed model of the sun pulsates with activity, showing sunspots and active regions. The idea is that you're not just a passive spectator, but an active participant, interacting with global events in real time.
And humans and AI work together.
Yes, our sources describe this as a world-first approach that uniquely combines human experts, the actual meteorologists and space weather analysts, with sophisticated AI avatars, all working in a united team to deliver the most accurate and contextually rich news. It's a fusion of human insight and AI processing power.
And it's not just prepackaged news or old data, right? This hub will be pulling in live, real-time data feeds from multiple global sources.
Precisely. The hub is designed to ingest and process massive streams of live data from various authoritative sources in real time. This includes APIs from organizations like NOAA, NASA, and the USGS.
So you see solar wind flares, quakes, all live.
Exactly. You'll see live solar wind data, current sunspot numbers, the latest solar flare classifications, geomagnetic activity levels, and even real-time earthquake catalogs, INSAR ground deformation maps, and radon sensor readings. All of this crucial dynamic information will be displayed intuitively and interactively within the VR experience,
Ensuring the news is always current.
and directly reflective of planetary conditions.
So, why does this matter to you, the listener? And how does this new paradigm truly change the way we consume critical information about our planet and space?
It's about making incredibly complex scientific data accessible, engaging, and highly personalized in a way that traditional media simply cannot. It transforms how we consume critical information, moving beyond passive observation to an active, immersive learning experience.
Seeing it happen instead of just reading about it.
Exactly. Imagine seeing a powerful solar flare erupt on that holographic sun model, and then immediately seeing its projected impact on Earth's magnetosphere, all while a virtual news anchor explains its potential disruption to satellites. It empowers you to visualize, explore, and truly feel the relevance of space weather and Earth's dynamic systems in a way that fosters deeper understanding and retention.
One of the most powerful aspects of this technology, especially with the use of multimodal LLMs, is their ability to dynamically tailor the narrative for different audiences. How do these models personalize explanations and adapt their communication style?
Well, one of the most powerful uses of LLMs here is their incredible ability to dynamically tailor content. Imagine being able to literally select your target audience within the VR environment, from kids under 12 to expert, and having the LLM instantly adjust the vocabulary, complexity, and depth of explanation accordingly.
So you could get the simple version or the super technical one.
Precisely. For a younger audience, to make it relatable, it might explain a CME as "the sun burped out some plasma," a playful, memorable analogy. But for an expert, or for you, our well-informed listener, it would immediately shift to precise scientific terms like an X-class solar flare producing a full halo coronal mass ejection with an estimated velocity of 1,500 kilometers.
Making sure it's always at the right level.
Exactly, optimizing comprehension for you.
That's incredibly adaptive, going beyond just age. And it sounds like it incorporates regional relevance and even sentiment analysis from external data sources.
Yes, the customization goes even deeper. The system can also dynamically tailor content to specific regional interests. For example, for an audience in India, it might focus on the space weather's potential impact on monsoon patterns or agricultural systems.
Or power grids in North America.
Exactly. For users in North America, it might prioritize potential impacts on the power grid or aviation routes. Furthermore, a highly innovative feature is its ability to analyze external data, like social media feeds, for public sentiment.
Sentiment analysis to see if people are panicking.
Sort of. If there's a surge of public panic or misinformation trending about a specific event, the AI can flag it to human editors for review. It can also suggest adapting the narration style, perhaps using a calming tone for public-facing messages during a high-alert event.
Acting as an early warning against rumors.
Exactly, and a tool for responsible information dissemination.
So what does this all mean for the listener? How does this deep customization benefit us in understanding and engaging with complex scientific information?
This deep customization ensures you get the most relevant information in the most understandable and digestible way possible. It transforms complex science into something truly accessible, fostering adaptive learning by allowing you to delve deeper into explanations or simplify them as needed, all on demand.
Learning at your own pace.
Exactly. It empowers you to learn at your own pace and in a way that resonates most effectively with your existing knowledge and immediate interests. It's about making science truly for you.
To truly make these vast, often invisible forces visible and comprehensible in VR, the environment uses interactive visualizations with what our sources call controlled exaggeration. How does this technique work, balancing scientific accuracy with compelling visual impact?
Right, to make subtle or vast phenomena comprehensible within the immersive VR environment, the system employs what's called exaggerated scales and a level of detail LD scalar. This is crucial for effective visualization.
So you make small things bigger so we can see them.
Pretty much. For example, a real-world 5-centimeter ground rise, a tiny, almost imperceptible shift that might precede an earthquake, might be displayed as a few meters in the model for visibility within the VR space.
Okay, that makes sense.
Similarly, a subtle magnetopause shift, the boundary of Earth's magnetic field being compressed by solar wind, can be dramatically amplified to make it clearly visible and understandable to the user. This intelligent exaggeration balances scientific accuracy and data representation with the dramatic impact needed for intuitive comprehension.
And it sounds like these aren't static images, but incredibly dynamic effects that truly bring the science to life.
Yeah.
What kind of dynamic visualizations can we expect?
Exactly. The visualizations are designed to be highly dynamic and responsive. For instance, magnetosphere visualizations will dynamically change shape in real time in response to incoming solar wind pressure, compressing and expanding as the forces fluctuate.
So you actually see the impact.
Yes, allowing you to intuitively grasp the impact. Solar flares and coronal mass ejections will be animated eruptions erupting from the sun with incredible visual fidelity. Crucially, time compression will allow you to witness a CME's 150 million kilometer journey from the sun to Earth in mere seconds.
Condensing days into seconds.
Right, condensing days of travel into an understandable moment. Auroras will glow and dance dynamically on Earth's poles, and the system can even overlay them in an augmented reality environment like the Apple Vision Pro.
Wow, auroras in your living room.
Potentially making it feel as if the aurora is directly in your own room.
And there's also a 4D time LOD feature, adding another layer of control. What does that allow us to do within these simulations?
This 4D time log system allows you to manipulate the timeline of simulations with unprecedented control. You can choose a detailed, slower progression of a CME for in-depth study, pausing and zooming to examine specific interactions, or you can opt for a rapid jump to key moments for a quick overview of an event's entire life cycle.
So you control the playback speed and focus.
Exactly. This dynamic control ensures the experience is smooth and effective on all devices and for all audiences, allowing for tailored learning and exploration. It means you control the narrative flow based on your learning needs.
So why does all this matter? Why go to such extraordinary lengths to visualize the invisible forces of the cosmos and our planet?
It transforms abstract data into a compelling, understandable visual story. It strikes a crucial balance between scientific accuracy and dramatic impact, helping you intuitively grasp complex phenomena that are otherwise impossible to see with the naked eye or understand through static charts.
Making the invisible visible.
Exactly. It makes the cosmos tangible, engaging multiple senses, and creates a memorable, deeply educational experience. It's about truly understanding the forces that shape our world.
This level of advanced visualization isn't just being applied to external phenomena like space weather or geological shifts. This raises an important question. What if we could apply this same groundbreaking visualization technology to something as complex, abstract, and internal as human consciousness itself? This brings us to the fascinating concept of the aura of intelligence, aiming to create a digital twin of consciousness. Can you elaborate on this incredibly ambitious project?
This is an incredibly ambitious and forward-thinking concept, really pushing the boundaries of what we consider data visualization. The Aura of Intelligence aims to create a digital twin of human consciousness, designed to be mapped onto a 7-layered nested toroidal structure with chakra representation.
Okay, 7 layers, toroids, chakras. Break that down a bit.
Think of it as a dynamic, multidimensional, interactive mind map, or maybe a life tapestry rendered in 3D. Each of the 7 layers could represent different dimensions of an individual's experience or aspects of their being, perhaps their physical sensations, emotional states, intellectual processes, creative output, or social interactions.
Like different facets of yourself visualized.
Yeah, exactly. These layers are interconnected and constantly evolving, allowing for a holistic visualization of one's inner world. While the chakra framework is a conceptual organizational structure, the core innovation lies in mapping and interacting with complex personal data visually.
And how would the system visualize personal narratives and the vast amount of data points that make up a human life? What does it look like in practice?
Well, this interactive VR model would visualize personal narratives and data points in a truly unique way. For instance, the red torus, which conceptually correlates with the base chakra, could represent early life experiences. Basic human body functions, foundational mind activity, childhood observations, and formative environmental interactions.
So you could sort of fly through your own life data.
In a way, yes. As a user, you could interact with this structure, manipulate it, and embed new information or memories, creating higher dimensional vectors that represent new connections or insights. It would also leave a trace address record of your experiences and interactions, allowing you to trace the evolution of your thoughts and feelings over time.
Providing a spatial way to see your own history.
Exactly. A spatial, intuitive way to interact with your own personal history and present state.
So it's like an incredibly advanced form of life logging, but with a fascinating twist towards self-reflection and potential benefits, especially in sensitive areas like mental health and aged care.
Precisely. It integrates reflective journaling prompts that are subtly aligned with the user's experiences and relevant conceptual layers, enhancing self-reflection without explicitly using spiritual terms unless chosen by the user.
So it guides you to think about things.
Yes. For instance, after a particularly stressful day, the system might prompt, reflect on how this experience impacted your sense of stability or grounding today. You can even pin favorite interaction sequences or moments of insight in the virtual space for quick access,
Saving important moments.
making personal revelations and breakthroughs easily retrievable and reviewable. The aim is to foster a deeper, more tangible self-understanding.
If we connect this to the bigger picture, this incredibly ambitious project seems to represent a holistic approach to visualizing and interacting with complex personal data. What are its potential applications beyond just self-understanding?
This holistic approach has profound potential applications. Beyond individual self-understanding, it could revolutionize areas like mental health, providing new diagnostic and therapeutic tools for conditions like anxiety, depression, or PTSD.
Letting therapists see the inner landscape.
Allowing therapists to visualize and navigate a patient's internal landscape, potentially. For aged care, especially concerning conditions like dementia, it could help individuals recall memories and interact with their life story in a tangible way.
Or help caregivers understand.
Or even help caregivers understand the progression of cognitive decline. It's about providing new ways for individuals to interact with, process, and even heal from their own life experiences, offering a truly empathetic and intuitive interface to the self.
Building on this idea of intelligent systems, our sources talk about mixture of experts and autogen agents. This sounds like an AI dream team collaborating to build these complex simulations. What exactly are these AI experts doing in this simulation environment, and how do they interact?
This is a truly sophisticated application of AI underpinning projects like the Aura of Intelligence. It involves the development of a simulation environment with AI GPT agents, where each agent is essentially an expert in their respective fields.
So an AI doctor, an AI ethicist, etc.
Exactly. Imagine a diverse team of AIs, where one is an expert in healthcare, another in ethical AI, a third in quantum computing, and so on. Their purpose is not just to provide information, but to actively simulate complex human behaviors and interactions within these virtual environments.
They role-play and solve problems together.
Yes, they can role play, analyze scenarios, and contribute their specialized knowledge to solve problems, much like a human multidisciplinary team would.
So it's not just AIs talking to each other. It sounds like humans are also crucial to the loop, ensuring accuracy and ethical development, right?
Yes, a human-in-the-loop approach is absolutely crucial and central to this system's development and operation. This allows for continuous human feedback to refine function definitions and agent interactions, ensuring continuous learning and adaptation.
Humans keep the AI on track.
Essentially, yes. Human oversight is vital for steering the system, validating its outputs, and ensuring its ethical development, especially when simulating sensitive human behaviors or assisting in critical areas like healthcare. It's a symbiotic relationship between human intelligence and artificial intelligence.
And what are some of the real-world applications of these multi-agent systems that our sources highlight, particularly in critical areas like care?
Our sources highlight specific and incredibly impactful examples. They describe the development of caregiver agents, therapist agents, and health analyst agents that would form a virtual integrated care system for aged care and dementia.
AI agents helping with dementia care.
Yes. These multi-agent systems are designed to provide valuable insights into real-world problems and scenarios. For instance, a caregiver agent might simulate different care approaches, a therapist agent could model therapeutic interactions, and a health analyst agent could predict health trends.
All working together to optimize care.
Exactly. All working together to optimize patient care pathways, provide support for human caregivers, and offer insights into managing complex conditions. This leverages AI not just for information, but for predictive modeling and scenario planning in critical human services.
Wow, what a journey we've been on today. We've journeyed from the sun's fiery breath, shaking our planet with high-speed solar winds and powerful coronal mass ejections, through Earth's subtle geological tremors, and even explored the moon's profound gravitational and potential electromagnetic influence.
It truly highlights the incredible convergence of cosmic phenomena, Earth's dynamic systems, and the digital frontier. From predicting space weather impacts on our technology to anticipating earthquakes with ever-increasing accuracy.
And even exploring the profound mysteries of our own minds through digital twins.
Exactly. The pace of innovation is breathtaking. It's about gaining mastery over the information that surrounds and defines us.
And what's fascinating here is how the same technological advancement allowing us to predict solar flares and earthquakes forces external to us are also being refined to map and interact with the intricate patterns of human experience and consciousness, our internal worlds.
It's a powerful convergence. The tools we build to understand the universe are also helping us understand ourselves.
As we continue to build these digital twins of both our planet and ourselves, what new forms of reality and self-understanding might emerge? How might engaging with a digital twin of your own life's experiences, reflecting your memories, emotions, and growth, reshape your perception of your own journey?
Connecting your personal narrative to the grand cosmic tapestry we've explored today.
Exactly. It leaves you with a lot to ponder, doesn't it?
Jerry bar, neon strands, thorium power in my sense. Dakini codes, goddess rise. Neon glow, soul secret code. United we thrive. Raise the vibe. Sun and sand, tide and wave. Power up, cosmic ray. Civilization of sand, solar prophecy hand in hand. Neos, magnets, and monoxide finds, quantum mantra, silicone mines, titanium shell, thorium core, clean and safe for sure. Breathe, hold, expand, release. You'll get ignite. Feel the heat. Malone bust cliffs. Sunrise complete. Kardashev 1, sparks ignite. Titanium sands, neon lights. Bikini pulse, love on the winds. Thorium sands, clean nuclear trends. Quantum echoes, kiss my lips. Micronova, heat wave grips. Sacred sands, sacred lore. Binary tantra, open the door. Gajra earth unlocks in time. Tantric circuit, the pulse divine. Solar memory, data combined. Encoded prophecy. Is it almost time? Waves push and pull. Tides rise and fall. Sacred myth, comprehend it all. Super intelligence just in time. Clean green energy for a dime. Quantum moments, stellar design. Bikini souls, hearts divine. Neon sky.